Today we want to look at some more at the definite integral and area, reading the definite integral as area. We had an interesting thing happen yesterday because we integrated a function and found some area. Then we integrated under a longer interval and found that the amount of area went down. And we theorized that it might be that when the function went negative, the definite integral counted area as negative. Which is exactly what happened. So let's review. We integrated from 0 to 2 the function 4 minus x squared to x. We found the antiderivative 4x minus a third x cubed and evaluated from 0 to 2. So there we are doing f at b, or capital F at b minus capital F at a. And we got 5 1/3, if I recall correctly. And we interpreted this by thinking of the graph of the parabola. So when we get this 5 1/3, this is the integral from 0 to 2 of 4 minus x squared to x. And that indicates that the area under 4 minus x squared and above the interval from 0 to 2 on the x-axis is 5 1/3. So that means that we're thinking that this area here is 5 1/3. Then after this, we calculated the integral from 0 to 3, and we got a smaller amount. So we saw less area from 0 to 3 than we had from 0 to 2. So we found there's less area from 0 to 3 than there is from 0 to 2. But then we observed what happens. Before x equals 2, on the interval from 0 to 2, the function is positive, and on the interval from 2 to 3, the function has gone negative. So then we observe that the function is positive, 4 minus x squared. So the function that we're integrating, the 4 minus x squared, is positive on the interval from 0 to 2 and is negative on the interval from 2 to 3. So there was speculation that the area from 2 to 3 is being counted as negative. So let's find out. Let's find the integral, the definite integral from just 2 to 3, and see if that is the difference between the 5 1/3 and the 3. So these observations led us to speculate that maybe the definite integral reads the area under the x-axis as negative area. Let's find out. So we're going to take 4 minus x squared, and we'll integrate that from just 2 to 3. Look at what's happening from 2 to 3. We've already got the antiderivative. So we plug in the 3, we get 4 times 3 minus a third of 3 cubed minus f at a, 4 times 2 minus a third times 2 cubed. Based on the numbers that we had calculated before that I failed to write down from yesterday, today, so we have to do it over again. This is 12 minus, let's see, 27 divided by 3. 12 minus 9, that's 3. That's this one here because we had plugged in 0. So here we get 3. Green is spoken for in this particular problem. Here we get 3. And here we get 8. 8 minus 8 thirds. So 8 minus 8 thirds. Well, that's right. I started at 0 specifically so I wouldn't have to calculate this again. Yeah. So notice that if we take 3 minus 5 thirds, that is the difference that we were looking for. 3 minus 5 thirds is negative 2 1/3. And so that's what happened. The definite integral when the function we're integrating is below the x-axis, the definite integral calls that area negative. And so we accumulated 5 1/3 units of area from 0 to 2, and then from 2 to 3, we lost 2 1/3 units of area, leaving us with 3 total. Question? How's everybody? Okay. Let's label some stuff that shows up in our fundamental theorem of calculus. So I have the integral from 0 to 2 of 4 minus x squared to x. So this 4 minus x squared, that's my little f. That's the little f. A is 0, b is 2 in this integral. And so our capital F is 4x minus a third x cubed. That's our capital F. If we set up our little f, in this problem, our little f is 4 minus x squared, and our capital F will be 4x minus a third x cubed. We got capital F by doing an antiderivative. So what this means is if I take the derivative of capital F, I should end up back at little f. So what we notice is this is how we got this in the first place, is that little f is the derivative of capital F. So let's remind ourselves about what we know about the derivative and the sign of the derivative, because the function that we're looking at, this parabola, this is the derivative of the capital F function. This is the graph of f. So this is the graph of f. but that means it's also the graph of f prime. It's the derivative of the 4x minus a 1/3 x cubed. On the interval from 0 to 2, capital F prime is positive. On the interval from 2 to 3, capital F prime is negative. So what we're going to see is that on the interval from 0 to 2, since capital F prime is positive, the function will increase. On the interval from 2 to 3, capital F prime, the derivative, is negative, so the function decreases. So our area down here, the area itself is 2 1/3. But the definite integral looks at area under the x-axis and says that's negative. The definite integral says negative 2 1/3. When we read area, we should always read that as positive. So the area is 2 1/3, but the definite integral is going to call that negative. So what we can do now with this information is modify what we had before. F prime negative means the function is decreasing. The area tells you by how much the function decreased. F prime positive tells you that the function is increasing. The area tells you by how much the function increased. Let's make a table of values for our function capital F. So if I look at f at 0, I'm going to get 0 because I picked 0 to be the constant. Then at 2, the value of capital F is 4 times 2 minus 1/3 times 2 cubed, or 5 1/3. At 3, the value of capital F is 3. I left off the 1. I wanted to put 1 in there. We haven't calculated 1, but at 2, capital F is 5 1/3. Then at 3, capital F was 3. So capital F goes from 0 to 5 1/3 on the interval from x equals 0 to x equals 2. We knew that capital F was going to increase on that interval because the derivative, capital F prime, was positive on that interval. We knew how much that capital F was going to increase because that is the area that is under the curve from 0 to 2. From 2 to 3, capital F prime, the parabola, is negative. So that means capital F is decreasing, and the area is telling us by how much. So here's that decrease of 2 1/3. From 0 to 5 1/3, there's that increase of 5 1/3. If we evaluate the function capital F at 1, fill in this blank, we get 4 and negative 1/3. That's not how we normally report that number. We normally call 4 and negative 1/3 3 and 2/3. If we find the integral from 1 to 2 of 4 minus x squared, that will be the difference between 3 and 2/3 and 5 and 1/3. Any questions? 5 minus 3 is what? 2. 1/3 minus 2/3 is negative 1/3. So 2 and negative 1/3. So we can add to what we were remembering about sign and direction. When f prime is negative, the function is decreasing. The area will tell you how much the function decreases. If the derivative is positive and then the function is increasing, the area tells you how much. That derivative stuff that we were talking about before is connected to the integral stuff that we're talking about now. Any questions? TLDR, we just added to our sign of the derivative, direction of the function. We just added to that. When the derivative is positive, then the function is increasing. The area will indicate how much. When the derivative is negative, then the function is decreasing. The area tells you by how much. Any questions? Comment? Snide remark. It's weirdly sunny and warm today. Kind of out of character for October, but I mean, which is really weird. I don't know if any of you ever played D&D, but one of the things that some DMs do is describe the weather that's going on. And they have tables for it, so it's not completely random, right? So you have a table and then like you roll for kind of a direction. So it's like a little bit more rainy than yesterday, or it gets a little bit warmer than yesterday, but it doesn't like completely change. Then I realize it's perfectly fine to just have a fucking random table for the weather if your game is set in San Bruno. It's like, oh, let's roll for weather. Rain. Next day, roll for weather. Sunny and hot. In normal situations, we're like, oh, that doesn't make any sense at all. But in San Bruno, I could be like, oh, yeah, okay. Whatever. That was all pause to make you let it sink in. That when the derivative is positive, the function is increasing, and the area tells you by how much. When the derivative is negative, the function is decreasing, the area tells you by how much. We can also simulate how hot it is by doing this. So if you're filming, you can't see what I'm doing on Zoom, but I'm shaking the screen and making it look like wavy lines or underwater. If you're really subjected, so if you're really easily manipulated, then I can say, imagine that you're under cool water. We have underwater math class. And so that's why the screen is wavy. I get motion sickness too, are they? Too easy. I can't really look at this. Anybody seen the movie, The Blair Witch Project? It's a really old movie. It was one of those early movies where it's like found footage, right? So it's like all filmed on handy cams. It would be phones now. Phones, and it was also before image stabilization. So like, I think if you like run along with an iPhone now, the phone will just like, oh no, I'm just gonna smooth this all out. But before, if you were running along with the phone, the screen would be like, oh, it'd be like, run. But now they just attach the camera to the actor, and it's like the stuff moves. But like the camera, you know what I mean? You know what I mean? You know what I mean? So anyway, people were like, oh, it's so frightening, this Blair Witch Project with this found footage, right? Ooh, did they really find this footage and stuff like that? And I couldn't watch the movie, not because it was scary or anything, but because the camera wouldn't fucking stay still, and I was getting motion sickness. I was like watching the movies, like, oh, I can't watch this. And they're like, oh, Leach, it's not scary. I know, but the camera will just keep moving around. These fuckers watch too much NYPD Blue. Camera moves around. Someone would be like, oh, wow, do you think that was real? It's like, well, how many hours of footage did they have? Like, well, how many hours of footage did they have? Like several hours. How many batteries were they carrying for their phones? And like, oh, or their cameras. And they're like, oh, you know what I mean? You know what the amazing part of the phone is? The most amazing, hardest part of the phone to build? It's the battery. Carrying around power is the hard part. Building small computers, that wasn't really a big problem. That wasn't hard. The hard part was having enough electricity for the thing. Early laptops had a kind of a big problem. They would burst into flames because like, oh, here's a small battery. Great. And it works for, as soon as you start doing too many things, the computer just like, I think Samsung had that problem for a little while. It's the battery. Early cell phones were the size of a briefcase. So you're like, oh, I'll carry your, oh, check it out. What's that? It's my phone. Imagine a classy briefcase, not some backpack. And it's like, ah, let me make a phone call. And there's like a wire connecting the handset to the backpack. The backpack was the battery parts, not like the antenna or the electronics. The phone was all contained in the handset. The backpack was just the battery for the phone. It's like, well, hey, what's going on? Yeah, I'm calling you from the street. You got to hurry up. I've only got like 20 minutes of talk time on my battery. Yeah, but the battery only weighs like 40 pounds. So, hello? Oh, I ran out of battery. All right, that's my old person moment for the day. Let's do a new problem. That was all just paused. The area tells you how much. That's what we added. We have this old stuff. The area is telling you how much. Let's look at a different problem. I'm going to draw a graph of f prime. So it's going to be, that's going to be 2, 1, 0. I'm going to draw the graph of a function, and it's going to entirely consist of line segments. It's going to be a line segments graph. So this is the graph of the derivative of little f. The reason that I pick line segments is that it makes area really easy to calculate. I've got rectangles and triangles, and those are easy areas to calculate. Because remember what we added to our previous observation. When the derivative is positive, the function is increasing, and the area tells you how much it increased. When the derivative is negative, the function is decreasing. The area tells you how much the function decreased. Let's look at what we can read based on the graph of the derivative in this case. I see that f prime is negative from 0 to 2, because the derivative is just below the x-axis. So first observation, f prime is negative on the interval from 0 to 2. So that tells us that f is decreasing on the interval from 0 to 2. On the interval from 2 to 5, we see that the derivative is positive. So that tells us that the function is increasing on the derivative on the interval from 2 to 5. I'm going to modify this slightly. So that's the first thing that we would notice about what's going on here. I had to modify that because the derivative is not actually negative when x is equal to 2. The derivative is equal to 0 at 2, and the derivative is equal to 0 at 5. So we are decreasing right up to 5, but we are not decreasing or increasing at 5. Other things that we can read based on old information is that the derivative is increasing on the interval from 1 to 3. So our function is going to be concave up on the interval from 1 to 3. So other things that we note is that f prime is increasing on the interval from 1 to 3. So that tells us that our function is concave up on the interval from 1 to 3. We also notice that on the interval from 4 to 5, f prime is decreasing. The derivative is decreasing, so our function will be concave down. So f prime decreasing on the interval from 4 to 5 tells us that the function is concave down on the interval from 4 to 5. Notice that f prime is flat on the interval from 0 to 1 and from 3 to 4. So our function will be linear, no concavity on those two intervals. This is just reading the sign and the direction of the derivative. All this information is just reading the sign and the direction of the derivative. But we have added more information to what's going on. We know that when a function, the derivative is negative, the function is decreasing. The area tells us how much. So if we can find the area in all these values, we can see how much the function has changed. We can see not only that the function is decreasing, but how much the function is decreasing. So let's calculate some area. From 0 to 1, we have a height of 2 and a width of 1. So the area here is -2. We wouldn't call the area -2, but we're going to be talking about definite integrals, and definite integrals call area below the x-axis negative area because the function is decreasing. On the interval from 1 to 2, we've got this triangle. It will be half the size of the rectangle, so just -1. On the interval from 2 to 3, now I've got a derivative that's positive, so my function is increasing. The area will tell us by how much. The area of this little triangle is a 1, so this will be an increase of 1. From 3 to 4, we have an area of 2 above the x-axis, so there'll be an increase of 2. And then from 4 to 5, we'll have an area of 1, so we'll have an increase of 1. So the area tells us how much the function is changing. Sign tells you direction, area tells you amount. I can use this to start building a table of values and eventually a graph of the function f. So we know how much the function is changing from 0 to 1. From 0 to 1, we should see a decrease of 2. From 1 to 2, we should see a decrease of 1. From 2 to 3, we'll see an increase of 1. From 3 to 4, we'll see an increase of 2. And then from 4 to 5, we'll see an increase of 1. Because the area tells us how much the function has changed. Why did I not fill in values for the function? If by your silence you mean there's no way we could have known that, that is correct. Let's suppose that I said I drove south for 400 miles. Where did I end up? Unless I tell you where I started or where I ended up, you can't tell. I just said how much I've changed. I just said how far I've gone. I didn't say where I started. I didn't say where I was when I started or where I ended up. I just said I drove 400 miles south. From where? So we don't know from where. That's the plus C parts. I have to tell you where we started. I have to tell you something about where we started. Oops. We only get the changes from f prime. We need more information to know where we start. So if we had some information about the function, we would be able to figure out what the plus c is. This is the plus c showing up in numbers. That's how the plus c shows up. We need an additional piece of information. We took the derivative of whatever the constant term of our function was, and we got 0, just like every other constant. So this is the plus c thing. So here's the graph of f prime of x. If I give you one of these values, so if I said, here's the graph of f of x, if we're given that f of, let's say f of 3 is equal to 0, that's information about the plus c. Not specifically what the plus c is, but it gives us a place to start. So if we're given that f of 3 is equal to 0, now I can figure out the rest of the values. From 3 to 4, we see an increase of 2. So f of 4 is equal to 2. From 4 to 5, we see an increase of 1. So f of 5 is 3. From 2 to 3, we see an increase of 1. So f of 2 must be negative 1. From 1 to 2, we see a decrease of 1. So that means f of 1 must be 0. And from 0 to 1, we see a decrease of 2. So we must have started at 2. The derivative is telling us about the changes. It doesn't tell us where we're starting. Any questions? How's everybody okay? Y'all are more resistant to mind control than my other classes. That's how I could tell. See, normally what happens is you do mind control. It's very limited mind control. But in the second half of the class, if I go like this, at a time when you're all looking at me, I can make some of you turn your head and look at the clock. Go like this, and everybody's like, oh shit, Leach knows what time it is. Now I need to know what time it is. And so you're like, oh, but I can't do it when he's looking at me. You're like, or you check your watch. Or you check your phone, because I can make you want to know what time it is. So they're like, oh. Okay, so with this information, we could draw a graph of our function. So I could start off at 2. At 1, we'll decrease down to 0. At 2, we'll decrease by 1 to negative 1. At 3, we'll be back up at 0. At 4, we'll be up to 2. And then at 5, we'll be up at 3. So we got this down and that and up. Here we see the function decreasing on the interval from 0 to 2 and then increasing thereafter. If we want to include more information, we know that the function was concave up on the interval from 1 to 3. And concave down on the interval from 4 to 5, and then linear in between. So I've got these two line segments. I got a concave down from 4 to 5 and then concave up from 1 to 3. We also notice that here, this minimum, this local minimum at 2, which makes sense because we've got the derivative equals 0 at 2, and the derivative is changing from decreasing, from negative to positive, so the function is changing from decreasing to increasing. Here at 5, we don't know what happens after 5. But we know the function is concave down before that, and the function is flat at 5. So my question would be, I just said that we don't know what's going on after 5. What could happen after 5? That's the question. That's it for today. I will see you all on tomorrow. Everybody have a good day. Figure out what could happen after 5, and thanks for playing.